Hello and good morning to our next calculus class, where we are continuing our discussion on exponential functions. We ended with the natural exponential function last time, but we didn't really do as many examples as I would have liked. So let's just look at a couple more to help us remember and just make sure we got the hang of this E function. All right. Oops. Okay. So I just want to see, where did we end up last time? Let's start with an easy-ish one. Let's look, for example, at y equals negative 16e to the 2x plus 1. Now, what makes these perhaps a little bit tricky is there are no brackets to indicate the presence of a function. But the more I look at these, the easier and more recognizable they'll become. So when I have my variable not alone in the exponent, then it's going to have to be a function of a function. So I now want to slowly transition at the same time as introducing this new exponential function. I want to perhaps just see how it feels if I write a little bit less when I look at the chain rule. So previously we would have defined our inside function as the obvious choice. Then our y function would be negative 16e to the u. With this negative 16, they're just trying to trick me. My derivative, which is the derivative of y with respect to x, is going to be constructed in two parts according to the chain rule. First part, we can casually say the derivative of the outside function, which is just a constant times a function property, then the derivative of the exponential function, and now the only thing in the exponent is the variable u, nothing else. So then the derivative is the exponential function itself. Originally, I couldn't do that because it wasn't alone. There was a function of a function happening first. Then the derivative of the inside function, which is 2, and I finish it by just replacing the u with what it is in terms of x, because that was really my choice to use that to help me find the derivative. I don't have to, but I want to just mention it to see how you feel about it. Because in some situations, it is a little bit clumsy and it is longer to define the inside function. You then rewrite the outside function, set up the chain rule, and so on. As I get more comfortable, I could say, well, okay, the inside function I see here, what the chain rule says is, remember, two parts. Let's put boxes around it. The chain rule is still going to come in two parts. The first part, I now am more comfortable, hopefully, and I know what it says, sort of casually in words. It's the derivative of the outside function with respect to the inside function as if it's one variable. So for the purposes of the first part of the chain rule, I don't look at the detail of the inside function. Call it u, call it whatever you want, but it's one single thing, as if that thing is the variable. What I then have is negative 16e to the something. Whether that something has a name or not, it's one thing. And the derivative of negative 16e to the something with respect to that something is negative 16e to the something, whatever that something is, because that something is now seen as the variable. Times, says the chain rule, with the derivative of that something. Okay, now I have to go look at it and see what is the detail of that inside function, that something. Oh, it's 2x plus 1. Its derivative is 2. And I can finish it. I'm just running out of space there. By inserting what the detail of the something is that previously we called u. But technically, you don't have to name it. It helped us in the beginning, but decide for yourself when you are ready to let go of it and just talk through it in the same way as we've done it, without writing all the steps. You don't have to make that transition, but it's okay if it naturally happens. Don't force it. If you're not comfortable talking through it like I just did, you need to see the U, set up the chain rule, then please do that. Don't force this or you're going to make mistakes. But I just wanted to mention that we can shorten our answer for the chain rule. Let me look at one more. There are, of course, many examples in the problem book. I'm going to look at this guy. These might actually be in the problem book. I am just making them up. Doesn't really matter. So here I see something interesting that's worth seeing in a relaxed paced setting. There's clearly a function of a function happening here. Whether there are brackets here or not in the exponent, and there rarely are, I need to see it and recognize it as a function of a function. So I'm going to write out, when this is a little bit more complicated and I'm not sure, I'm going to help myself. If it's straightforward, like before, then sure, maybe try not writing everything out. But if you're unsure in any way, or the function is a little bit more complicated looking, play it safe. Be sure, whatever that requires. So if I let u be the inside function, then my outside function y is going to be u times e to the u. I can certainly do that. That is a correct breakdown of the function of a function. But is it the best choice moving forward? I claim it's not impossible. I can totally do it this way. But it's not ideal. It's not optimal. Why? Why? How come? Because this outside function is still tricky. Perhaps it's less ideal. Still needs a fair bit of work to find the derivative. So when I am looking at the chain rule, this is going to be the first part. This guy is not as simple as it could be. You can totally do it, but I see a lot of mistakes happening when the first part of the derivative, because the variable is different and it's a little bit more difficult to wrap your head around what's happening here. I want that guy to be as easy as possible. And this one, meh, could be better. So instead, I'm going to first get these two away from each other. Yes, they look very similar, but this is not my preference. So first, I am finding the derivative. I'm going to use the product rule first. So it's the derivative, and again, you don't have to write this step, but in order for the video to look good and your notes to be complete, it's not a bad idea to write out a little more than we may need. we don't want to get through with the bare minimum. See more so that when you look at this a month from now, it's clear. The derivative of the first times the second plus the first, whoops, brackets there, times the derivative of the second. So what the product rule has helped me to do is isolate these factors. So I don't have to look at the derivative of all of it, but just individually. The downside being that, okay, I have multiple terms, but that's not that big a deal, really. So now the first one's super easy, 2x, and the e to the x squared plus 3 stays. The bracket is still there. Now I have a much simpler derivative of an exponential function. Yes, there's a little chain rule in here, but it's manageable. It's e to the something. First part of the chain rule, take the derivative of e to the something with respect to that something. Because it's e to the something, the derivative is e to the something. I don't look at the detail of that something. Really, I see a blob. I don't really care what the detail is. But of course, eventually I have to write the detail. I don't pay much attention though. The derivative says times the chain rule says times the derivative of the inside something. Now I look at the detail, see it's x squared plus 3, so the derivative is 2x. Again, if this is not comfortable for you yet, you can say let v equal x squared plus 3. Let's call this g, and then g is e to the v. So the derivative of that little piece is set up, oops, it's a b, by the chain rule to help guide me in terms of what to do. And now I see when I look at this first part, it's just e to the variable. So the derivative is e to the variable. It's the simplest derivative I could possibly get, times the derivative of the inside function, which is 2x, and I get the same thing back, right? More detail is not bad. I'm just saying, if it happens naturally, you want to drop some of the detail in applying the chain rule, you can totally do that. Just make sure you're still safe. Okay. If someone gives you another problem like this and your reaction is, it's so easy, I'm so tired of this, then you've mastered it. But if there's any flicker of hesitation when you look at these functions, you're not ready. You need to practice more. But only you can decide that, right? I can only give you advice. Whether you take it is up to you. Next topic. Well, this is still really part of the same discussion, but next little subtopic. I'm going to map this out for us. What have we done here? This is our map, and this is what I think about. We have the general, that's ugly writing, but still, general base exponential function. Y equals a to the x. That's where we started. Let's put a box around it. We tried finding the derivative by way of the limit definition. We kind of got stuck. And what turned out helping us was this wonderful and weird number e. So then we said, let's just stop looking at this in general and let's just look at this specific base and call it the natural exponential function. And let's just narrow our view a little bit here. Just handle this guy. Its derivative, oh, I did not leave myself space, I'm sorry. Its derivative we could find. It's the simplest thing possible. It's the same. Great, that's wonderful news. It's so natural to just write down the same thing again. We don't know what the derivative exactly looks like in the general case. So we do have to come back to this. But it was too big of a question to answer at that early stage. So we changed it. Or not changed, we simplified it, looking at a specific base, E. Just turns out that E is a weird number, yet the simplest. So weird. Okay. This exponential function, or the exponential functions, there are many, of course, is only half of the picture. It's only half of the picture. Because let's look at the exponential function e to the x. So now remember, I have now this as a basic function in my library. Let me just emphasize this to the point where you are sick of hearing me speak, but it is so important. Let's graph it. The fact that I have base e doesn't change the general, the basic shape of it, right? It could have been a 2 to the x. The basic shape is this. Now, this little guy is going to come up over and over and over for the rest of the semester. It's arguably the most important function for early calculus. However, I see people every single semester not being able to graph the basic exponential function. And not even graph it. Just close your eyes. You have to know the shape. You have to know there's a horizontal asymptote on the left. It approaches infinity on the right. Y-intercept of 1. You have to close your eyes and picture the shape if you want an easy time moving forward. And so many people, they don't have that skill, knowledge, I don't know, that picture. And then things are so confusing because it's going to happen. A month from now, I'm going to ask, close your eyes. Can you envision the basic exponential function? Then we just read off the answer. It's so easy. But if you can't picture it, then you have nothing. And your life is so hard. Take my advice, please. Make this easy. Okay, so that's one side. Side note, I know. But I say these things because they can hold you back so much or make your life so easy. You decide. So I have this exponential function. There it is. It's smooth, it's nice, it's not too hard. It's a simple shape. Okay, I don't have a lot of symmetry, but it's pretty simple curve here I am looking at. I can ask the tangent line question, derivative question. Everything's good. Okay, everything's good. So now let's pause this. Pause. And remember something in pre-calculus. Remember inverse functions. Oh no. Do we remember inverse functions? Maybe. That's a good answer. I like that answer. Maybe. The word is familiar, but don't really ask me to do anything. That's the level we are probably at. Don't ask me to write down anything, but I could remember the word. That's okay. However, we're not doing a lot with it, but it is required to link to the rest of the discussion. So I'll just do it by example. And as I do it, maybe it becomes more familiar. So let's just pick a function that we can draw easily, like 2x plus 3. Should be pretty straightforward. Let's draw it. Just a straight line. There's no need to make this complicated. So the straight line is going to have a slope of 2 over 1, y-intercept of 3, so it's fairly steep, so let's put it over here. That's a pretty good line that matches it. So this is now my line. Let's name it over here. 2x plus 3. So now the question is, what is the inverse function? So let's call this f of x to make it look more familiar. How do I find the inverse of this? Oh, come on, stupid line. So to find the inverse function, there are quite simple steps. Swap x and y. So let's do that. So then we have x equal to 2y plus 3. I just swapped x and y. Y's become x's, x's become y's. All right. And then second step, solve for y. So let's do that. So 2y equals x minus 3. So y equals 1/2 x minus 3 over 2. Let's graph that. I'm gonna zoom out just a touch. So let me graph that. Roughly over there. So this is now the line, y equals 1/2 x minus 3 over 2. So graphically, the relationship between these, by the swapping action that we've done, is we've created the mirror image in the line y equals x. Y equals x. So apart from the function relationship between the two, which we'll get to in a second, graphically, we've created this mirror image. Okay? So I want to keep the graphical relationship of these two in mind as well. But what is the function relationship? So now I'm going to call this guy f with a -1. That's if my function's name is f, the inverse is named with this -1. It doesn't mean it's the reciprocal. It's not 1 over f. It's just, sadly, an unfortunate naming system. It's just a name. F to the -1. We don't say f to the -1. It's not. It's f inverse. So, okay. So what are the properties of the function and its inverse? Is it looking a little more familiar, maybe? Maybe a little. I don't know. So there are really two things that I want to know. I don't care about how to find it, really. I want to note the relationship graphically of the function and its inverse in terms of the graphs, and then the relationship between these two guys, the functions themselves. Come on, stupid line. I'm gonna make a new page. I'm running out of space here. This is annoying me. Let me just make a new page. The inverse function has got nothing to do with the derivative. It's another way, it's a function linked to a given function. If my given function is, what was it? I can't remember. 2x plus 3. Let's take a simple guy, right? There's a function. I can make any other function. Then it has a friend called the inverse function, and we found it. That's our way to find it. 1/2 x minus 3 over 2. 1/2 x minus 3 over 2. It just has a friend. It's not the derivative, just a friend. Everyone needs a friend. Graphically, that friend sits sort of opposite the diagonal line y equals x. I have another function, it has another graph, but they're linked to each other. They're connected in some way. They're not two random graphs. They are mirror images of each other in this diagonal line. Okay, so graphically, there's a very strong connection between the two. Another connection is, oops, I'm in eraser mode here, that if I compose these two, what does that mean? It means create a function of a function. So I'm going to take the outside function and apply it, sorry, the first function as the outside function and the other function as the inside function. What do I get? Well, I work inside out. So I apply this 1/2 x minus 3 over 2 first. That's the inside. Then f is applied to that. What does f do? F takes its input, multiplies it by 2. So let's do that. And then adds 3. So now when I multiply the 2 in, I get x, I get minus 3, and then this plus 3. So I get x. What does that mean? That means that something is being done to input x, and then when I do the outside function after that, I've done nothing. I get the original input back. So nothing has happened. So these two, in the composition sense, they cancel each other. If I apply one of them, and then on top of that apply the other one, I cancel whatever the first one did. And literally nothing happens. I can do it the other way around, because we saw that composition of functions, the order matters. I can do the same thing. I will leave that to you. I get nothing. I get x back. So if whatever my input is, I get it back. Even though these functions individually do something to the input, right? You could see it. Something's happening. Things change. The answer is not just x anymore. The x is in a calculation. Yet when I do one and then the other one on top, it cancels that effect, and I just get the original input back. So they cancel each other. Though graphically, it's not obvious that that is what's happening. Okay, so maybe that sounds a little more familiar, just a little bit. We don't need to remember everything about inverse functions. We simply need to have that concept in order for the exponential function discussion to move forward. So, back to this. Let's zoom back in. I have this guy in my library. It's my exponential function, my favorite exponential function, the easiest one to work with, base E. It's a graph. It's there. And when I put the line y equals x as a dotted line with it, it sits well above it. It doesn't cross it or anything. Even if it crossed, it doesn't matter. There's a graph, which means I can reflect it in this line. What is that reflection going to look like? Can you visualize that reflection? Can you see it when I flip it in this dotted line? Hopefully you can. It's going to look like this. So there is another graph here. It has an x-intercept of 1. It has a vertical asymptote. And it just keeps going to infinity on the right. Not as fast as the exponential function, but it is going up. So they're both going to infinity and beyond. I can't help myself. I have to say. So there's a graph. The exponential function has a graph. I can flip it. There's another graph. And I know this graph is the inverse. So this is the graph of the inverse function of e to the x. It's there. I can see it. It has properties and everything. I just want to name it. That's all I want to do. I want to name it. We're going to call this the natural, because it's coming from the natural exponential function, logarithmic function. and it's going to be y equals ln for natural logarithmic function of x. Technically, there are brackets here because that's a name, but the convention is to not really show the brackets, just a little space. This is just a name because this function doesn't exist in my current vocabulary. It's not a polynomial. It's not nothing. It's not a rational function. It's nothing. It only exists because of its connection to a function I already know, the exponential function. So we had to just name it. Now, technically in the history, the order of how these things were discovered is a little different, but whatever. This is the easier of the versions. It exists. It's connected to a function I already know, but I just have to name it. So someone somewhere decided on the word logarithm, natural because it's base E, ln is the name. It's just a name. It's just a name. Okay. So now I have another function. Let's uh, let's squeeze in the properties here. If x approaches infinity, then for this guy, y approaches infinity. It doesn't grow as fast, but it grows. It never stops growing. So that's one. And then the vertical asymptote. If x approaches 0 from the right, then y approaches negative infinity, vertical asymptote. It's undefined for x less than or equal to 0. See, it doesn't cross this y-axis. It's only half of the space. It's half a graph. Because of how it was flipped. Because what was flipped? The exponential function. And then I get this situation. So now, new basic function, there it is. Which means I can do transformations on it and do whatever. And it's all built on this basic graph. So now there are two of them. Because one has an inverse, creating another one. And that's as far as our inverse discussion really goes. So now I have two of them in my basic function library. The exponential function, close your eyes, see it, picture it, see its properties, read it off as you picture it while you're closing your eyes. Very important. I now want to be able to do the same thing for this natural log function. Close your eyes, picture it. You can make the association between the graphs with the flipping, sure. But it's nice if it can be a standalone graph in your mind. It's at the bottom, coming close to the y-axis. At the top, it's slowly increasing, and it's crossing the x-axis at 1. Not a hard graph, but you make your life so much easier if you can visualize the graph and read off its properties. Because it's going to happen. It's going to come up. And it just makes everything so much easier. Now, I'm going to skip doing a transformation on this, but you can, for example, where can I write? You can, for example, try something like y equals 2 natural log x minus 1 plus 3. You should be able to do that, right? I don't feel that I have to do it. You just break it up, make the sequence of transformations, and build it. Whoopsie, where am I now? Build it on this basic graph. So that really should not be a problem. Okay. I want to continue the discussion past a side note of transformations. Okay. What we're now going to really have is the other side of this picture, where The other side of the natural exponential function is the natural logarithmic function. Y equals ln of x. You could say log of x. Some people say ln of x. Sort of really the only two options I'm interested in. Yeah, so eventually we're going to worry about the derivative. Not yet. Not yet. Not yet. Not yet. Just want to get used to the log function and its relationship to the exponential function. So things are happening very fast here. Just yesterday, we introduced the natural exponential function, and now I expect you to be perfectly comfortable with it. That's unfortunately how things go, because now we're introducing a new function. And to best understand that function, I'm building that understanding on the exponential function. So I need to make that one solid first before I can build on it, of course. Okay. So now I understand the link between inverse functions. If I have one function and its inverse, then they are linked by way of composition and they cancel each other's effects. Okay. But now I have that. I have a function and its inverse. I don't care what they're named. I have this exact situation. So something that's very important is the understanding the link between the exponential function and its inverse, the natural logarithmic function. They are inverses of each other. That's where they came from. Inverse functions, which means this cancellation property is true. So that means that if I do one inside the other, I should get x back. And if I swap the order in which I do that, I still get x back. They cancel each other. Now, if I forget the name f and stuff here, but use the actual functions, let's maybe do it this way. Let's get rid of these dots and write it on this side. So this one is going to be, I'll do a temporary version, f of natural log of x, right? I'll update that in a second. Actually, it's updated over here. F is e to the something, whatever the input is, it's e to that. Now the input is the natural log, so it's e to the natural log of x. So this guy is e to the natural log of x equals x. First property. The bottom one, man, that wood chipper is really loud. Let me know if you can hear it. I can hear it, but sometimes on the recording it doesn't actually create a lot of background noise. But let me know if you find a lot of background noise. I can't even hear my own voice, but these microphones are so nice they don't pick it up. Let me know. So in this direction, I have f inverse, and the inside function is e to the x. So e to the x. So that means in this logarithmic function, the input is e to the x. So that means it's natural log of e to the x. Now, you don't need brackets, but I think brackets are nice there. Natural log of e to the x is x. Okay. So these two properties are very useful. They're going to come up numerous times. And all it requires is an understanding of the relationship between the exponential function and the logarithmic function, and the fact that they cancel each other. Right? Now, some people choose to just memorize this. I don't love that idea, but there's nothing wrong if you just want to memorize that. It's going to be okay. It's going to be okay. There are a couple of other properties that logarithmic functions, that this logarithmic function has, that's actually very interesting and somewhat counterintuitive. I don't have a lot of space here. Let's perhaps, I don't want to overwhelm you. We only have 7 minutes. Let's delve into those properties tomorrow and focus on the derivative instead. Now, there's good news and bad news here. What do you want to hear first? When it comes to the derivative of natural log of x, there's good news and bad news. The bad news is that I cannot explain why the derivative of the logarithmic function is what it is. We don't have the tools to prove it. This one is not done by way of the limit definition. It's done with other things. And we don't have those tools in our toolbox. So it's a little unsatisfying. You just have to memorize it. And then later on, maybe a month from now, maybe a little more, uh, we are going to have the tools and we can come back and say, oh, now we can explain why the logarithm has this derivative. So it's not terrible news, it's just bad. I didn't say it was terrible. The good news, however, is it's super easy. The derivative of the natural logarithmic function is 1 over x. Now, it looks weird, and it is. How can the derivative function be a rational function, and the basic rational function on top of that? But the original function was not polynomial based at all on the surface. These guys actually are connected to polynomials in a more complicated way. But like I said, I can't explain why it is. Given the tools that we have right now, there's no way I can explain it. It just is. But before the course is done, we will be able to come back and prove that it is 1 over x. And it's actually not even that hard. It's just a matter of where you're at in your journey. So let's just practice that for our last few minutes and just get used to the derivative of this new function, which is another basic function that you should have in your library. And I understand these things happen very fast. Like in a couple of days, we just introduced 2 new functions. It's not the easiest thing to get on top of so quickly, I understand. I'm just looking for some nice examples. These are way too hard. Wow. I don't want to do any of them. I was going to make up my own examples. I don't want to waste time opening the problem book now. It doesn't really matter. Let's say y equals natural log of 2x, let's say cubed plus 1. So now it is a little bit better that I see brackets and I can better identify the function of a function. Just note that there's a big difference between this, actually I'm going to write 2 functions here, and this. And that's something no one is going to tell you. You just have to magically understand the way we write these things. If there are no brackets, then after the ln, only the very next term is applied to the logarithm. If more terms should be in the logarithm portion, there need to be brackets. These 2 functions are not the same. Don't be neglectful with your brackets. They are there to make clear what we mean. So these are completely different. This one's first. So let me perhaps, this is our first time on this function, so let's have our help u, because this is a chain rule situation, right? And the obvious choice here is 2x cubed plus 1. Then my outside function is natural log of u. If it helps you, put brackets there. Totally fine, doesn't matter. This is just a name. I can never have it on its own. It is meaningless on its own. It's meaningless on its own. It needs to be applied to something. If that something is a single term, you don't need brackets. But if you want to have brackets, that's cool. Do it. So my derivative by way of the chain rule can be made and found in two pieces. That's what the chain rule allows me to do. The first piece is the derivative of the outside function with respect to the variable. Well, I have it right there. Natural log of something, derivative is 1 over whatever the something is. If it's a single variable, right? Same as the exponential function issue. Nope, that's not what I want to look at. Where am I looking? Oh, here. Right there. If it's a single variable, just like here, it was a single x, then the derivative is e to the x. If it's a single x, then it's 1 over that x. If I call the variable a u, well, that doesn't change anything. It's single. Then it's just 1 over that. Second part of the chain rule, I'm going to look for my u function. So it is going to be 6x squared. Finish it by writing what the u actually means. Now, some people like to put the 6x on top and make it one single fraction. I don't like that because it makes it look as if it makes me forget the order in which I did things. And while I'm thinking of this, there are probably people that when they do the chain rule, they do the inside function derivative first and then the circle one. It's not wrong because it's multiplication. I can certainly swap these two, but the time is going to come when you're going to make a mistake. And I just want to warn you. There is a specific order to this. The outside function is addressed first, then the inside function. Not mathematically required, because multiplication can be swapped around. But to avoid mistakes, I strongly encourage you to do it in this order. I know there are always people that swap them around. It makes no sense to me why you would want to do that. It's not logical. The chain rule is never introduced like that. It's never backwards. Even though I can swap them around doesn't mean I should. So, side note there. Outside function first. And to help myself remember how this was constructed, I don't put the 6x squared on top. If I leave my answer, I'm done. I'm moving on. Because it makes it seem that other stuff has happened that didn't actually happen in my construction of the answer. All these little things. Ooh, so many little things. So when I now look at the second function here, different function, only this part is in the logarithm. There's more to it, sure, but in this case, my inside function is going to be 2x cubed. It certainly still is a chain rule. It could be a chain rule first, sure. Then my outside function is, I'm just going to finish this one, then we're done, is natural log of u plus 1. If you're not sure how to read this, use brackets. The plus 1 is separate from the logarithmic portion. So my chain rule says, set it up, always outside function first. I've never done the inside function first, ever. I don't know where people might get this, but I know you're out there. You're going to make a mistake. Don't do it. Derivative of the outside function. Now the outside function is simple enough, right? I have a sum property here. I have a constant function property there, but they're not really going to be major players here, right? It's still 1 over u because I can isolate that term. So there's no harm in that. And then times derivative of the u function, which is 6x squared. Now, it looks a little deceptive here because this extra portion was so simple that the answers look the same. But the functions were not the same. Plug in x values, calculate it. It was not the same. I just happened to choose a very simple second portion, which falls away in the derivative you see there. So it's a little bit deceptive. But that's what happens when you make random examples, right? It's still not the same. It just looks the same. It's close. It's not the same. The answers are not the same, right?
All right. That is where we'll have to pause for today. Of course, this discussion continues and expands across the exponential and logarithmic functions. Are there any questions at this stage? Right, then we will continue this tomorrow, and by the end of the week, we'll have the whole picture completed. Until then.